Hi, Tiara. You're
Hello.
there. Hello.
Yes.
How are you?
I'm okay.
Good. Good, good, good. Have you started either one of those quizzes yet?
Yes, I just got finished doing the one that's due today.
Okay. All right. Did you have any questions about that?
I have a few. I'm not sure if I did anything correct except for the first three questions. Because
So
after that,
you're worried about maybe the last one where I said you do a power series of this one if you know that the second derivative of this is blah, blah, blah?
yeah, I didn't realize you told us that because I went through like making sure that they were actually like the same, taking the antiderivative multiple times. And then I was like, oh. And then I went back
Yeah.
and I saw that you basically told us that. And I was just
So ultimately all you have to do is write the power series for 1 over x plus 1
yeah.
and then take two derivatives.
I figured that out like 5 minutes before class. I was like, wow.
Okay.
I wasted 20 minutes doing.
All right. Okay, good. Who's that? Who's waiting? Dion's waiting and Deborah's waiting. So anything before that? Anything? What else?
The tangent one kind of threw me off because I feel like my answer's too easy.
I don't know whether it is or not. Well, yeah, because listen, when I gave you the series for inverse tangent or tangent, whatever it was, inverse tangent, and that's one of the ones where you can find a series by using the series you already know. So if I ask you to
okay, so then I think I did what I.
So what did you tell me what you did?
I mean, well, the only difference was there was an X. So basically I pulled that out and put it in front of like what tan inverse of X.
Or you just, in other words, you just multiplied through what I gave you by an X. And that would be those would be the terms.
Yes.
Okay, that's fine.
Yes, that's okay.
I mean, when you're creating
when
you're creating a series from an already given series, it's easy. Okay, because you just have, for instance, if I had e to the x in a series and I was asked for e to the 2x, I would just go through the series and everywhere there was an x, put a 2x. Okay.
I was just like, this is too easy. She would never give us something like this.
Yes, I will. I did, and I'll give you something else like that too. But because it would be hard to do that and find derivatives of it. Okay. So anyway, okay, I got everybody in. Deborah, I got your power series quiz. I could not figure out how to get it in my grader to begin with, and after I fiddled with it and sent you an email and said I can't do it, I did it in the next 5 minutes. So you got it? Did you get it? You got everything? You understand what you did wrong?
I think so.
Okay, all right. The one I saw that was the major one is that you had a 3 in that number 1, and that needed to be over there when you were looking at the endpoints. Okay, it was x times 3, and then less than 1, and then when you divide by 3, you got less than 1/3. And so that was the interval, not 1 to -1, but minus 1/3 to 1/3. Okay. Who else do I need to talk to? Let's see. Who's not here? Alexis is not here yet. Dion, you doing okay? Down there. Doing okay? I see an eye tip poking up over there. Yeah. She's rubbing her eyes. Not supposed to touch your face. Remember that? That's what I've been doing all day long, rubbing my eyes because I'm tired of looking at the computer screen. So guys, we're going to do something totally different today, but give me that power series representation quiz. And sometime today, I want to finish grading it tonight and get it back to you. And then the other one tomorrow was just doing one of the Taylor series and a Taylor series and a Maclaurin series, a Taylor series and a Maclaurin series. And they were just like the problems I did yesterday, very similar. Like I think I did one yesterday that was 2 to the x. Well, the one I gave you on the sheet was 3 to the x. Okay, so I don't think, probably won't have a whole lot of trouble with that. The one that is the messiest on that one is the tangent. So you have to do 2 or 3 derivatives. Make sure you get those derivatives right. It's going to be chain rule, product rule, that kind of stuff. Okay. Any other questions? Any questions? All right, let me share the screen. I want to ask you some questions about a couple of things, and let's see what we got here. So I want you to take your calculators out right now, and I want you to do the following. I'm going to kind of move off to a different page here so I can get a page at the end. Okay, all right. So, so here's what I want to look at. Oh, come on. I want to know on your calculator what you would do to graph the following. Suppose I said graph x squared plus y squared equal 4. X squared plus y squared equal 4. First of all, what is that the equation of? What's the graph of that look like?
Circle.
It's a circle. You're right. It's a circle. What's the center of that circle?
0, 0.
Yeah, it's 0, 0. Remember, if we write it like this, the thing that you subtract here is your center. What's your radius here, guys?
2.
2, because this looks like radius squared. So if that's radius squared right there, then clearly the radius is 2. So we know what it looks like. I mean, it looks like that. It's got a radius of 2. It's centered at 0, 0, blah, blah, blah. But if you wanted to graph it on your calculator, what would you need to do? And it's this one right here. What would you do with that? If you wanted a full graph of that on your calculator.
Square root of 4 minus x squared and the negative square root of 4 minus x squared.
Okay, so Deborah says, look at what you're solving for y, Deborah. Is that what you're doing? Okay, so if I solve for y here, guys, I'll get y squared is 4 minus x squared, which means y would be plus or minus 4 minus x squared. And so I'd have to graph it in 2 pieces. I think I have to graph it in the first piece would be the plus part of it. Can you tell me what that would look like if you graphed it on your calculator, the plus part, and then you can tell me what the minus part would look like. What would this one look like? Okay, Deborah's doing this. She's saying, watch, what's she saying, guys? Somebody give me words for her motion.
Half a circle?
It's half a circle, and it's the top half, isn't it? Because it's where y's are positive. And what's this one going to be?
The
Bottom half.
Going to be the bottom half. Okay, now I'm going to test out some software on you, and we'll just do it. So we're going to I'll try to put it on the calculator, but I'm going to try to share my screen with something else other than what I've got right here. So this is going to go away for a little bit. I'm going to go to my apps here, and I'm going to go down and look at, what am I going to look at? This thing right here. Thing. And I'm going to go with a new share. And that new share is going to involve this thing right here. And let's see what I can get on that. Okay, there we go. My screen is paused, and can you guys see it yet by any chance? Can you see anything up there?
No.
Okay, well, let's see. Let me resume my share then. Come on, get going here. I'm gonna pull that out. Tell me when you see something. Okay, new share. Let me try it again. Something. Okay, what do you see? Tell me what you see.
Yes.
So I see a calculator on the right, and I see a graph on the left, okay? All right, calculator works just like your calculator, except it's a kind of a little bit of a fancy calculator. It gives me all my pictures in color and nice things like that. But what I want to do is I want to graph what we were talking about a second ago, and I'm gonna let Alexis in right now, and she's gonna be in the middle saying, "What's she doing?" Okay, and I'm gonna clear that. What I got in there. Okay. And I'm going to put in the top half of that circle, and then I'm going to put in the bottom half of the circle. So I'm going to hit second square root, and I'm going to put in 4 minus x squared, I think is what we said. So 4, whoops, wrong. I'm going to delete that. I'm going to say 4, and the minus is going to be that. Oh, I lied. It's going to be that one right there. Gosh. I keep trying to type on my keyboard, guys, and that's really, I need to type on the calculator and not the keyboard. So 4 minus, I'm gonna pick up my X, I'm gonna square it, and then I'm gonna graph it. And I don't know what my window looks like because I know what we're looking at. I think I'm gonna change my window from -10 to -4. And then I'm gonna change it to 4. I'm gonna keep a scale of 1. I'm gonna go -4, down to 4, and still scale of 1. And I'm gonna graph the top half of that circle. Okay, now, it doesn't look very nice, but you probably know what to do to it. And I'll do to make it square up in a minute, because there's a command for that. The next thing I'm gonna do is put in the bottom half of that circle. So I'm gonna go down here. Alexis, are you with us? Alexis, did she get in? I don't think she got in, but she's not answering me. I'm gonna put in a minus there. And so that's gonna be minus, and then my square root again. And I'll put in the same thing, the 4 minus x squared. And that. And then I'm gonna graph that. And there's the whole circle. Now, guys, it looks like an ellipse right now, but that's just because the pixels on this thing aren't evenly spread out across the board. So I'm gonna go to zoom. I'm gonna go to zoom 6, which says zoom standard. No, that's not what I wanted. I wanted zoom square, zoom 5. It'll square up the screen so it really looks like a circle. So there's a circle. Okay. All right.
Carol, Alexis said her computer is working slow.
But she can't see what I've got?
Yeah, she said something's wrong with her computer.
Oh, okay. It's not wrong with mine, it's wrong with hers. Can she hear me? Ask her if she can hear me. Okay. So circles are a little hard to do in what we call a rectangular coordinate system. We kind of have to split it up. And one reason is because this thing is built to take functions, all right? So if I wanted to do something that was a figure 8 on this thing, that might look really hard because it's not a function, and it might be a really complicated y equal a function of x, and I might have to graph it in 2 pieces like this. But what I want to do right now is show you another mode I can put this calculator in, and then we're going to work with that with a different kind of coordinate system. So right now, I'm going to go to the mode key, and I'm going to go down. I currently have this calculator in function mode. That's why we had to enter this in 2 different parts, because if you look at the whole thing together, it's not a function. Top half's a function, bottom half's a function. Put them together, you don't have that. All right, she's trying to get in again. Let's see. Okay. Yeah, okay. All right, I think she might be there.
Yeah, I'm here now.
And do you see what's on the? Can you see what's on the screen, Alexis?
Yeah, I'm on my phone.
Oh, okay. So do you see the calculator and so forth?
Yeah.
Okay, good. All right. So guys, I'm gonna put this in a whole different mode, and it's a whole different way to graph things. And that's what I want to talk about today. I just want to introduce it, and then we'll do more with it. It has nothing to do with series. So the next test, there'll be this little bit of material hanging over on this new system here. We'll do what we can with it, but this next test will only have series on it. Okay, and we'll talk about this later, what we're going to do later. But I'm going to move it over to where it says polar. Okay, I'm going to enter polar mode. I'm going to put that in polar mode. Now, I want to show you what this y equal looks like when I have something in polar mode. So I'm going to go back up. I move down. I put it in polar mode. I'm going to go back up and hit y equal. Now, you do not see y equal anymore. You see R1 equal, R2 equal, R3 equal. I want to show you something that happens if I say R1 equal 2. Okay, R1 equal 2. And then I'm going to explain to you why it's doing what it's doing. If I have R1 equal 2 and I graph it, I get the circle. Okay, it's a circle. It was easy to graph. It was almost like as easy as graphing a vertical line or a horizontal line. Now, these are called, what I'm getting ready to talk to you about is called a polar system. You can graph all kinds of things with it. For example, if I said, let's graph 2, and I'll show you how it looks a little bit different too. 2 plus 2 cosine theta. Now, my variables in this polar system are going to be an r and a theta. And that you can kind of guess that the theta is going to stand for some kind of angle. And the r we're not sure about yet, but since r was 2, and we got a circle of radius 2, maybe it means something about how far away something is from the origin. Every point on a circle of radius 2 is 2 units away from what's on the origin. Now, I'm going to pick up my variable here right there in that xt theta n, but when I'm in polar mode and I hit it, you'll see a theta. Okay, so that's what you get there. Now, now I'm going to graph that. I mean, you have no idea what that's going to look like. You don't have any sort of feeling for this thing yet. But when I graph it, I get something that looks like that. That's actually called a cardioid. Can you tell me why it's called a cardioid?
Hmm?
Can you tell me why the word?
Looks like a heart.
Yeah, because it looks like a heart. Cardiology, cardiac arrest, cardiac. Okay, that's the Latin root for heart. Okay, this is
That looks like a heart.
it looks sideways. Okay, it looks like a kidney bean to me, but whatever, it's a heart. It's called a cardioid. There are things where you can draw them and you get this little loop in here. Let's see if I can create that for a second. Suppose I had 2, I don't know what this is going to do, but we're going to see. Suppose I had 2 minus, and suppose I put a 3 there instead of that, and I left the cosine there, and I graphed it. Okay, see how that one's a little different? It went all the way around, it did a loop, and then did that. That's called a limaçon. I'll spell it for you later, don't worry, it's a French name. But lima, that means it looks like you know what lima beans are? Everybody call butter beans, lima beans. That kind of looks like a lima bean, and that little thing right there is where it gets sort of punched in the middle there. You can graph all kinds of things here. Let me give you one more, and then we'll go back and talk about what this system does. All right, I'm going to clear that one. Oh, you know, there was one other thing I wanted to do. I'm going to put in r equal 3 this time, and I'm going to graph it, and you're going to see a circle of radius 3. So that's pretty nice. Every point on that circle is 3 units away from that central point there. We normally call that the origin. Okay. Then I'm gonna let you look at the window and see what it looks like. The window looks a little weird here because it's got a theta min and a theta max. Now, theta min and theta max are actually going to be things that are set a range on this angle theta. So I'm going to let that first one be 0. And I'm going to let this next one be pi over 2, let's say. Oh, phooey, it went away from the window. From 0 to pi, which is going to be right there, divided by 2. Now, you don't really know what I'm doing yet, but I'm setting a range on an angle here, and I think you'll see what happens when I do the graph. This step I'll explain to you later. X min, X max, we still have an X min and an X max and a Y min and a Y max. That still says you want a 10 by 10 screen or whatever. This other thing is setting something different. So I'm going to put in minus 10, and then I'm going to go down and put in 10. So I'm still looking at a 10 by 10 screen. All right. Now, I'm going to graph it. Now, notice that I left in r equal 3, which we saw was the circle centered at the origin with radius 3. What happened when I set that theta from 0 to pi over 2?
It showed it.
It plotted a quarter of it, didn't it? It plotted everywhere from the angle 0 up to pi over 2. Now, again, if I want this to square up and really look like a circle, I'll just zoom square it. I'll do zoom 5. Okay, so let me ask you this. If I'm setting this angle and I want 3/4 of the circle, I'm going to go back to the window, what would I set? Now, by the way, this took that theta max. I put it in as pi over 2. They changed it to a decimal, but I can still put it in as pi. Suppose I wanted 3/4 of that circle. What would I put in down here, guys? If I wanted 3/4 of the circle.
3 pi over 2.
Yeah, 3 pi over 2, because that's where 3/4 of it would be. So I'm going to go, no, I'm not going to do that yet. I'm going to say, I'll do pi. I'll go ahead and do that. Nah, let's clear that. I'm hitting the wrong keys here. I'll do 3. And then second, that thing will get me the pi. And then I'll divide by 2. And then when I go back to graph it, it looks like 3/4 of the circle. So if I wanted the whole circle, what would I put in there, guys? If I wanted the whole circle, what would I do with the window?
2 pi.
2
2 pi.
pi.
Yeah, I put in 2 pi. So I'll do it and we'll see what happens. I mean, it should definitely do that. So I'll hit 2 pi and graph, and it instantly graphs the whole circle. Now, so that theta sort of is plotting out some of the points on this circle based on the range of an angle. How about if I wanted the top half of the circle? What would I put in?
Pi.
I go from 0 to what? Top half?
Pi.
Pi.
I go from 0 to pi. What if I did this? What if I said in this second one, I put in 4 pi? Now, before I graph it, I'm going to see if I can get you to tell me what you think it's going to do. So I'm going to put in, let's see, that one, 4 pi. Now I've got this circle as going from 0 to 4 pi. Now, it only took 2 pi units to get it all the way around one time. What do you think it's going to do if I put in 4 pi? What do you think?
Go around it twice.
Yes, it's going to go around it twice. Exactly. You can't see that because it does it so fast that you can't really see that. But you really only needed a 2 pi to get around it all one time. Okay. So so let's talk about this thing called a polar coordinate system, and then see what we can learn about how we graph these things. Polar coordinate systems are nice for circles and angles, and clearly you're going to see that they use a lot of trig. All right, I'm going to go back out of this one and try to get my screen back up, guys. And I haven't perfected my technique yet with this, but I'm going to try to see what screen sharing has stopped. Okay, I believe that. I'm going to share the screen again with this other thing I've got. See what it does. Good, there it is. There's Alexis in the corner there. And iTunes can't read anything, and I really don't care. Okay, there it is. Okay. So let's talk about how we're gonna have this new coordinate system we're talking about. That's easy to graph things that like circles on. Okay, so I'm gonna go to, yeah, I went away from it. I'm gonna go to wherever I still was, which was my lecture 1 right there, and talk about what we need to know about this system. Okay, so what you're used to doing is graphing something with what's called a rectangular coordinate system. It's based on lines, basically. That's why you see that grid sometimes when you're trying to plot things. And you plot points by going a certain distance in the x direction horizontally and certain distance vertically up here. So the 0.25 is exactly where you think it is. Easiest graphs you can draw through the 2,5 would be a vertical line through 2, or or a horizontal line through 5. Get back down to here. So, I mean, you could certainly draw that thing right there. That doesn't mean anything right there. Okay. Whatever, we'll get rid of that. But those are sort of easy things, and it's easy to write the equation of a line. You've learned and used a million times y equal mx plus b. You know other things like y equal x squared. You know kind of nice things that are easy to graph because you plot these points. Now, what I was trying to show you a second ago is what we did when we tried to plot on a rectangular coordinate system, x squared plus y squared equal 4. We had to split it into 2 pieces and put a top half and a bottom half and say, okay, that's the best I can do. What we're going to do is introduce a new system called a polar coordinate system, where things are based on different ideas about how to plot points. And the basic parts are going to be angles and radii, distances from the origin. So I'm going to skip this part for a second. Here's what we're going to do. Instead of having a grid on an axis system and an x-axis and a y-axis, we're going to have what's called a polar axis right here, and the axis theta equal pi over 2. Now, guys, theta is going to be our points. Let me do this. Our points are going to look like r and theta. If we're in a polar system, the theta stands for an angle, and it's an angle that you start from in this standard position. So theta is some angle in standard position. That was what I was setting the window at. I was saying, let's let the angle go from 0 to pi over 2 and see what happens. Now, the r stands for the distance from the origin. So when we plot a point, we're going to find a point that's on one of these circles. Now, those are horrible. I'll get you some graph paper. I'll make sure you have graph paper to do this on. I've already put it on Moodle. These are concentric circles. They look horrible, but this is 1 unit away from the origin. This one's 2 units away. The next one's 3, and the next one's 4. If I ask you to plot the point 2 pi over 2, what that means is I'm going to take the angle and go up pi over 2, and then I'm going to plot the point r, the distance away from the origin. So there's the point 2 pi over 2. 2 pi over 2. Now, if I had said 2 pi over 4, our angle will only be up to 45 degrees, and I would plot a point right there on that second circle, and it would be 2 pi over 4. If I said 4, 0, if theta's 0, guys, I haven't gone anywhere with my angle, and I go out 1, 2, 3, 4 units, and I plot that point right there. Another one. Suppose I said 3 minus pi over 3. Now, I remember what minus an angle is. Minus an angle goes back in this direction. It goes clockwise instead of counterclockwise. Gonna have to remember some trig to do some of this stuff. And if I ask you to plot the point 3 minus pi over 3, you go back, you go on this concentric circle 3 out, you let your angle go down to minus 60 degrees, or in other words, minus pi over 3. So that point right there is the point 3 out from the center, and minus pi over 3 in an angle down to here. Now, there's something that causes the polar coordinate system to have some issues that rectangular does not. That 3 minus pi over 3 is not the only way to get to that point. In other words, there might be another representation for that point. I mean, if you look at the point 2, 5 on a rectangular system, there's only 1, 2, 5. You go over 2, you go up 5. There's no other way to say that. But if you're going around a circle, you know you can go around this way. You can go around counterclockwise with a positive angle, or you can go around clockwise with a negative angle. So tell me another way to describe this point right here. What if I went this way with the angle? It would still be on the same circle. It would still be on the concentric circle 3, but I could get to this same place by going how many degrees. Now, if this was minus 60, we'll do it in degrees, so I think you'll see it might be a little easier. If this is minus 60, where would you go over to here if you came in that direction? How many degrees would that be?
It'll be in the 3rd quadrant.
Well, not 3rd quadrant, actually. I think it's going to be in the 4th quadrant.
Oh.
Well,
300?
Yeah. Yeah, exactly. How far is it all the way around the circle, guys? 360, right? Or 2 pi. So if I've already taken up 60 going this direction, all I have to do is go in 300 to meet it over there. And if it's in radians, it'll be 5 pi over 3. So in other words, there are two different ways to talk about the same point. I would end up the same place if I got to it using an angle, a minus angle, or if I got to it using that positive angle. And these always differ by 2 pi. So for example, if I said, I want you to plot the point 2, actually let's do 4 and pi. Where would that be, guys? What circle would I be on?
Huh?
What does the 4 stand for? Remember, this is R and theta. It would be on the 1, 2, 3, 4 out from the center, and I would go all the way around pi units. It would be right there. So does everybody see what I'm doing? The R stands for how far away you are from the origin. And that's why these circles are convenient, because that tells you how far away you are from the origin on those circles.
So it doesn't have to be negative. It just has to be a number.
You mean the 4 or the angle?
Yeah,
The 4?
like the 4.
I will tell you about that in a second, because that's a great question. Let me leave it positive for right now. Give me a way I could get to the same point and change that angle, guys. What's another representation for that point?
4, 0.
No, I got to get around to the same point, but I'm just going to get around to it a different way. If it was pi in that direction, how much would it be in this direction?
Pi.
Okay, if it's 180 degrees this way, those are positive. That's a positive direction. What would I do to get that way? Remember,
Negative pi.
Yes, negative pi. Exactly, negative pi. So guys, remember, going around counterclockwise are positive angles, and negative angles go around the other way. So you can get to the same place, but these two always just differ by pi units, 2 pi units, 2 pi units. All right, let me do one more. What if I said, okay, I'm gonna try to remind you something I did a minute ago. What if I said 4, 3 pi? Pi is half a circle, right, guys? So if I went out to 4 and I went 3 pi's, there'd be 1 pi, 2 pi, 3 pi. That would be another way to represent it. All 3 of these points are in the same place. They're all in the same place. So there's a difference here. What it basically says is that in a polar coordinate system, you have multiple representations for the same point. And if you think about what I did when I changed that window a minute ago, from 0 to 2 pi, we said it mapped out the whole circle. And I went from 0 to 4 pi, it goes around the circle twice. So it's hitting all those points again with a higher value angle, okay? But they're the same points. Now, there is one weirdness about this, and it's this. It's exactly what Alexis was asking. This is very weird. It's always been strange to me, but I'm gonna show you something here. If I said, if I have a minus r in there, and this has to do with some properties of trig. If I have a minus r, you look at it and you say, well, that doesn't make any sense. It doesn't make any sense to go -3 away from the origin. And remember, that's what r stood for. But when I have a minus r, here's how I'm going to view that. All right, let me scroll down here, guys, for a minute. That's lousy. Let me go back to this one. When I have a minus r, if I had minus r 5 pi over 4, I would go to 5 pi over 4, which would be down here. But if there's a minus r, what it does is shoot it pi units straight across to the other side. It shoots it, it's definitely on the circle 3. But if the r is minus and it's 5 pi over 4, 5 pi over 4 would be in the 3rd quadrant right here. Straight across from that would be a pi over 4. In other words, a difference of 180 degrees, all right, or a difference of pi. What you can do is rewrite that one with a positive r if instead of this 5 pi over 4, you shoot back into the quadrant that's on the other side, or diagonally across, and use the angle that's there. Okay, that's weird. Let me put it on a better graph and I'll show you that. I'll show you what I'm talking about here. Let me see if I can find some polar paper here. I put some, let's see if that one works. Yeah, that one's crappy. Hang on. More polar graphs. So points have differing kind of representations. Hang on. I know I put some more polar paper in here. Ah, there it is, right there. Bingo. Okay, so guys, if I look at this, that's typically what polar paper looks like. If you go into your computer and you Google, I want polar graph paper, here's what you're gonna find. You're gonna find these concentric circle things that look like that. And if you'll notice here, the values that are on it are all those nice values from the unit circle. Remember the unit circle? Dr. Maddox, the unit circle and all of that stuff? That's that. This top point, this top thing is, of course, pi over 2. The bottom one is 3 pi over 2. But if I said, what I was trying to tell you a minute ago, if I said, I want you to plot the point -2, 4 pi over 3. If there's a minus r, you go out to that circle. In other words, you go out to the second circle here, and you go to 4 pi over 3. But if the r is negative, what it does is shoot it diagonally across to the other side, and that point can be represented as 2 pi over 3. That's weird, but that's what happens when you have a negative r. So that's the point -2, 4 pi over 3, and you could locate it down here, but if r is minus, you shoot it back to that angle right there. And let me show you another one. Suppose I said I want you to graph -1 pi over 2. -1 pi over 2. We'll get on the 1 circle. We get it pi over 2. But because the r is minus, I shoot straight back over this direction. So in other words, I'm at this point. So what's that the same as? It's the same as 1, and then what would that angle be all the way down there? See, if this is pi over 2, that's not a 1 right there. Sorry, I put it on the wrong circle. Let's get rid of that one and that one. So I would go to the circle 1, this first circle here. Pi over 2 would be right here. But if it's a minus, I bounce back straight across and do this point. And that point right there would be 1. And what would the angle be? How far is it around there, guys? How far is it there?
3 pi over 2?
3 pi over 2. That's just an
I'm just confused.
Well, it's an odd thing that happens. That only happens when your r is negative. When the r is not negative, it just plots out normally. For instance, if I said to you, I want you to plot 2 pi over 6. That's going to be on the second circle, and pi over 6 is right there. That point would be right there. It's only that when you have the negative, if you want that negative made into a positive, you have to shoot across to the opposite quadrant. That's all it is. You have to just remember that. That's what happens when you have that.
So the r, is it the height or like the distance? Because
it's the distance.
I was saying it two different ways. Like,
no, here, look,
oh,
it's the distance. Look at this circle right here. The definition of a circle is something that's the same distance all the way around from its center, right? And that's what a circle is. So the r that I'm talking about is the distance from the origin. So on every one of those circles right there, what's the distance from the origin? Well, it's actually 2 units, and that's my r. What's the r on this circle? Now that's 1 right there. Sorry, that's 1. What's the distance on this circle? How far is it away?
2.
2. Okay, so that would be the r for any point on that circle. What's this one right here?
3.
3. Okay, so those points would all have a first coordinate of 3, and then the angle would be depending on where you stopped. What if I said, where would the point 2.5, 7 pi over 6 be? Where would that be? Well, 2.5, remember, is the distance away from, and I'm going to get rid of some of this, guys. It's getting messy. Where would what does that R tell me there? If R is 2.5, where am I going to be?
In the second circle.
Well, you'll be somewhere between the second circle and what?
Oh, the third.
And the third circle, right? So in other words, you'd be halfway between the 2 and the 3. So 2.5 would be right in here. I have to kind of envision another line there. And then I would stop at what angle here, guys?
7 pi.
7 pi over 6. So I would come down here and I would say that point is right here. It's at 2.5 units away from the origin and 7 pi over 6. So that point would be 2.5, 7 pi over 6. Okay. So that's how I plot points here. Now, let me talk to you about, and some of the homework tonight is just practicing plotting points, okay? The pole, this is called, instead of being called the origin, it's called the pole. And if it's called the pole, it always has an R of 0. Well, why does it have an R of 0? How far is it away from the origin?
0.
0 units. And it can be any angle. Anytime you have an R equals 0, 0 pi over 2 is still right there. 0 pi is still right there. 0.3 pi over 2 is still right there because you're not going any distance away. It doesn't matter what the angle is, you're still right here. So that's the that's sort of our origin for a polar system. It's 0 and an angle. Okay. All right, let's go back and look at something here. Nope, I don't want to do that. Let me get back to my lecture here. Okay. So, all I've really talked about is plotting points and what these points look like. Let's go back here for a minute. I kind of want to know what the relationship, let me find it first, what the relationship between the rectangular system is and the polar system. So for example, suppose I said that there's a rectangular system and here's a point right there that goes out theta and is R units. That point right there in the polar system would look like R and theta. Okay. Now, if this happened to be X and that happened to be Y, it would also be the same point in the rectangular system. So what I want to know is what's the relationship between the rectangular system, the XY, and again, X is just that distance right there, Y is just that distance right there, R is just the distance from the origin. I want to know what the relationship is. Well, I can relate those really easily because look at this. What is the sine of theta, guys? Look at this triangle I've drawn here. What's the sine of theta?
Y over R.
Y over R, okay? Remember, it's opposite over hypotenuse. Yep. What's the cosine of theta?
X over R.
It's X over R. That's right. So there's a connection between an X and a Y coordinate and an R and a theta coordinate. Now, let's think about that for a second. Let's think about what R is. This is a right triangle. So that says X squared plus Y squared is R squared, which means R would be the square root of X squared plus Y squared. Okay, so there's the connection between R and it's the distance from the origin. If you look at that, guys, that's the distance from 0, 0 to X and Y. Okay. One more thing, and then we'll talk about how we convert things. If I said, let's put sine over cosine. Sine over cosine is a tangent. And we said that sine was Y over R, and cosine was X over R. So when I invert and multiply, I get Y over X. So there's a connection between the angle, again, and the Y and the X. If I apply the inverse tangent on both sides, I get this relationship. Okay, so I'm going to work with those 4 formulas I've got there, and I'm going to ask you some questions. Suppose I said I wanted to find out, and I'm going to look at this. I'm going to draw a little rectangular system down here. And I'm going to say, suppose I've got the point 1, 1 in a rectangular system. And I want to know what it is in the system R theta. So 1, 1 in the rectangular system means I'm just going to go over 1 and I'm going to go up 1. Okay, that's all it means. In R theta, I'm going to need to know what the angle is and what the side of the triangle is there. Because that'll tell me how far I go away from the center and what the angle is. Now, I don't think that's a big problem here. Look at the conversions. If I think about R, I think I could find R. And look at what I said R was. It's the square root of x squared plus y squared. That's using the Pythagorean theorem there. So that'll be 1 squared. My R will be equal to the square root of 1 squared plus 1 squared, because that's what that is, and those are the sides, which means R will be the square root of 2. So my R for that point in the polar system is going to be square root of 2, because that's how that you kind of see that, guys, just using the Pythagorean theorem. Now the next question is, what's the angle? You know, I think you could tell me what the angle was on this one, but I'm going to show you how to do it. But tell me, what do you think the angle is right there? If this point goes through 0, 0, and this line goes through 0, 0, and 1, 1.
Pi over 4. I don't really know. I'm just guessing.
Go guess. Yes, let's see.
I said pi over 4.
And you're right, because it's halfway up to pi over 2, isn't it? It's halfway up to pi over 2. It goes 1, 1. It cuts the quadrant right in 2. So the theta there is theta equal pi over 4. Now I'll show you how we could have. You can't see that. That's always not always that nice. So here's how we would do it. Look back at my relationships here. The sine was y over r. So in this case, the sine of theta, my y coordinate was 1, and my r was root 2, because that was just the distance. If I rationalize that, I get root 2 over 2. My cosine, my x coordinate was 1 over root 2, and that's root 2 over 2. Now you're thinking, oh, where am I on the unit circle if I get root 2 over 2, root 2 over 2? Where am I on that unit circle? I'm at pi over 4. So this point right here has a rectangular coordinate of 1, 1 and a polar coordinate of root 2 pi over 4. Okay, root 2 pi over 4. Let's try another one. Let's look at this one. Let's go from rectangular to polar again. I want to use one more. Remember when I put sine over cosine here? It was y over r over x over r. And that was sine over cosine, and that was y over x. That's the tangent right there. The tangent of the angle you're looking for is y over x. Go back and look at my rectangle, guys. If you look at my rectangle here, if that's theta, what's the tangent? What is a tangent in a rectangle? Opposite over adjacent. So it'll be y over x. So that's where this came from. Y tangent of that is going to be y over x. So let's go back. Let's go back to this 2, 3. Suppose I've got the rectangular point 2, 3. And I know that I can find r. You look at how far that point is from the origin, it'll be the square root of 2 squared plus 3 squared. I mean, think about it. If you're right here at 1, 2, 1, 2, 3, 2, 3, you're looking at a right triangle with a 2 for X and a 3 for Y. You can get R. You can get the distance right here by just looking at that, okay? So the square, R is 2 squared plus 3 squared square root. That'll be the square root of 13. So this is, R is 3.6, which means when I start to plot it, I'm gonna go out between the 3rd and the 4th circle, okay? 3.6. Now I need to know what angle it is, okay? I'm gonna use this to find that angle right here. So what's tangent of theta if this is the case, guys, if that's Y over X? What are Y and X here?
3 and 2.
3 and 2. All right, so that says tangent of theta is 3/2. Now, how do I find theta? Calculator, talk to me. Don't talk to me about unit circle because this isn't a good value on the unit circle.
Take
What
the
about
inverse.
take the inverse? Theta is the inverse tangent of 3/2. Now, guys, I want you to set your calculator in degrees. I want you to go to the mode key and set your calculator in degrees and tell me what you get for the degrees there. Do the inverse tangent of 1.5 and after you set the mode key in degrees.
56.3.
Okay, so Deborah's saying the angle's about it's about 56 degrees. Now I want you to set it in radians. Go back and set it in radians and tell me how many radians that is. What do you get for the radians, guys?
A definite.
Uh-oh. What do you, so if I were doing degrees, I don't usually do degrees. That's why I'm trying to get you to do it in radians. What do you get? What's the radians of 3/2 point? Wait a minute. Go down to, get my mode back. Go down to, I'm gonna go to radians and then I'm gonna hit, let's see, second quit. And then I'm gonna hit the inverse tangent of 1.5. Inverse tangent now, guys. Inverse tangent of 1.5, you should be getting 0.98. Is that right? Okay, so if I put this in radians, it's gonna be square root of 13 and 0.98. We usually do this in radians. We do not usually do it in degrees. Now, let me remind you of some markers and then I'll let you go. A marker on the axis system here, that's 0. 90 degrees is pi over 2, which is about 1.57. So it makes sense that since this was 56 degrees, it's 0.98 is right in there. Pi is 3.14. And 3 pi over 2 is 4.71, and 2 pi is 6.28. So if I say to you, my angle in radians is 3.5, then you know it's somewhere in here in the 3rd quadrant. If I say my angle in radians is 5, it's somewhere in the 4th quadrant. All right, finally, if you want to change something from polar to rectangular, that's easy too. Just there's your X and Y relationships right here. You know what R and theta are. There's R, there's theta. Put in your R, which is 5. Put in your theta, find the cosine, you'll have that. Want to find the Y, put in your R, take the sine of your angle, you'll have that. I got a lot more to say about this. There is homework in 2 places. I put some homework from another book in Moodle, but I want you to look at this and it'll be right at the end of the lecture, so you can fast forward it if you have to. I want you to plot some points on some polar paper, which I put some on Moodle, plot these points, change from rectangular, change to rectangular coordinates if they're polar, and change to polar if they're rectangular. All right. And we'll pick this up again tomorrow, okay? So there's a small homework assignment there, and then there's this one right here. Just scan, I can leave it, see, I can get it smaller. If you want to, I don't know, guys, if you want to stay on and write it so you don't have to go to the video, that's fine. These first ones are plot. These are go from rectangular, these are all polar, go to rectangular. These are all rectangular, go to polar. Okay. All right. And I'll have the answers. This is what we'll start out doing in class tomorrow. First thing you had to do when you were in the 7th grade, you had to learn how to plot points before you could do equations. All right, tell me when you're when you're done, okay? And you can leave.
I took a screenshot of it.
When you can,
Yeah, I took a picture.
you take a picture. Yeah, everybody can take a screenshot of it if you want to.
Bye.
You got your phone though, Alexis. That's not going to be. It's sort of small, but you might be able to do it. You might be able to see it. Okay. Look online for the polar paper. If you got a printer, print some of it out. If you don't, just get some. Look at a Google site, and there's a million polar coordinate things on the Google site. All right. Let's see who's still with me. Deborah, you're still with me. Dion, you're still with me. Now, Deborah, you're the only one that's with me. You doing okay? Whoops. Deborah, you got it? Okay. All right.